Very good. So, thank you very much. Thank you very much for having me again here at the Technologieplauscherl. My name is Rainer Stropek, and I'm a passionate programmer. I have been using C# for many years. I don't know how many, but since the very early CTPs and technology previews and so on, and for years I've been writing code in that language. Recently, in the last years, I switched a little bit, or let's say I enhanced my coding skills a little bit by taking a look into Node.js with JavaScript, TypeScript, Go, and so on. And recently I saw that, especially in C#, Microsoft is doing a lot of work in terms of memory management. I will talk a little bit about it. And I got curious. Where does that come from? What is the idea behind it? What is this trend that I'm seeing? And I took a look at Rust, and I found very interesting concepts that I wasn't aware of as a C# or JavaScript or Go developer. So I thought I share my thoughts and findings of my first adventures towards Rust and my comparison in terms of memory management of C# and Rust with you. Let me start by showing you a little bit of demo code and phrasing the general problem that Rust is trying to solve. This chart shows vulnerability and patches per year, and this white line that you see here and the dark blue area on the bottom is the number of vulnerabilities and patches with regards to memory safety issues. And if you can't read it, this starts here in 2006, and we are currently at 2018, and still nothing has changed. Nothing got better. We had approximately 70% of vulnerabilities related to memory safety issues in 2006, and we have roughly around 70% of vulnerabilities regarding memory safety issue in 2018. And this is an official study and that you can read. I have the link in the slides here. It's from Microsoft, and you can think of Microsoft whatever you want, but those guys aren't all completely stupid. So just sitting down and saying, okay, tomorrow I will write C++ code that doesn't have a memory leak, that doesn't do a double free, that doesn't do a use after free, is just not enough. We are just not good enough about compiling code in our heads. We need more support. And that's the basic problem. So let's take a look first. Before we take a look at the solutions, let's take a look at some of the problems. You will now see very ugly code, so be prepared. Just an idea. We have a method here. This is C++ code. Very ugly C++ code. Maybe I have written it. I don't know. No, I came up with it just to prove the point. As you can see, we are allocating a little bit of memory here in this getData method. We are copying some code in it, and then we return the buffer. And the user, as you can see it here, the user gets this buffer here and prints it on the screen. It doesn't matter, it consumes it somehow. And what do we have? A beautiful memory leak, because nobody is responsible for freeing that memory. Of course, if you see it on a single slide, everything is clear. You look at it and you know, hey, I forgot to free it. But think about more complex applications. I'm totally aware, and I want to emphasize that this is not C++ bashing. I'm totally aware of the fact that today in modern C++, you have lots and lots of functionalities to not having to write this code anymore. You have smart pointers, you have structures like vectors and strings and a lot of other things. I know, but still, I see code like that. Many people see code like that. That's a problem, and we will take a look how Rust makes it even better than makes these situations even easier to handle and detect than modern C++. Another problem. Here you can see we allocate a little bit of memory. We try to do some kind of SQL statement, for instance. Then when executing this SQL statement, something bad happens. See it here? And we free the memory. That's fine. But unfortunately, many pages later of source code, somebody has an if statement. If something happens, we try to do a logging and we use the statement which has already been freed. This is a typical use after free. And we all know we shouldn't do that because this is really a security vulnerability. Another example for use after free, and this time it might surprise you because it's C#. How can we do a use after free in C# if we have managed memory? That doesn't work. We never free memory, don't we? We have the garbage collector who cleans up after us well. It turns out that C# recently has learned a lot of tricks to make it more efficient in terms of memory management. And one of the tricks that C# has learned is, for instance, well, that's not recently. The recent stuff comes later. This is old stuff. Let's start with this one. I mixed up the order of the slides, sorry. This one, it's using the disposable pattern. A disposable pattern is necessary because if you have a garbage collector, you can never be sure when the garbage collector cleans up your mess after you. Therefore, you have this nice little dispose method which you can call explicitly to tell C#, hey, clean up. And therefore, I can write exactly the same code with exactly the same problem and accessing this connection although it has already been disposed. You know what C# will do if you do something like that? Object already disposed exception. Boom, runtime error. This is exactly what we don't want to see. Another C++ stuff. We have a pointer to an integer, as you can see it here. We clean it, as you can see it here. But we also call a method called printValue. We pass in this pointer, and this method here tries to be very, very clean and also deletes the pointer. And what we have is a double free problem. We should never do that because we have an undefined state in C++ memory manager and therefore bad things can happen. That's a security vulnerability. We don't want to be able to do things like that. Now this one is the new one. I mixed that one up. Again, a double free problem in C# which is absolutely not obvious. This is a recent one because the thing that I would like to point your attention to is this array pool here. Why is there an array pool? It turns out that C# isn't very good in handling large buffers, large arrays for instance. If you allocate a lot of large arrays, they are not handled in the usual way as C# usually handles memory. It turns out C# becomes a little bit unstable or not that fine to handle when you allocate a lot of arrays. You should really reuse arrays. And array pool is a way to ask C# to give you an array and to reuse it later on. So you can ask the array pool for an array in a certain size. It will give you this array. You can give it back. And if somebody else asks for another large array, this piece of code will get a reused version of this array. So you don't need to allocate a new one. This releases the pressure on garbage collector. And guess what? It's pretty easy to produce a double free problem here. Because if you do something like this, you have a return of this array here, and you have a return of this array at the same time. And you must not do that. A double free problem directly here in a managed language using the array pool. Okay, enough problems. Let's take a look at solutions. First, I would like to introduce you to some new concepts that have recently been added to C# version 7 and version 8. First, C# tries to solve a lot of the problems that we discussed before by introducing memory management, managed memory, and a garbage collector. You do not need to explicitly free memory. That's good. It solves a lot of problems, not all, as we have seen, but it solves a lot of problems. The big problems that C# introduces with that is performance. The garbage collector is not a zero-cost abstraction. That means you pay the price with performance. You never know when the garbage collector cleans up. You will never get the most performant code that you could write without this abstraction because the garbage collector is always guiding you and you don't have the control that you would like to have. But C# learned, as I said, a bunch of new tricks to really solve that problem on a very basic level. And now C# in the version 7, they added 2 new types in this regard. The first one is called span and the second one is called memory. And essentially what these 2 types do is they add an API for accessing different types of memory, especially unmanaged memory and managed memory, through the same API. And with this, if you really need in C# to access unmanaged memory, or with span even memory that lives on the stack, you can just work with span of t and memory of t and have an abstraction that is independent of whether your bytes live in managed memory or unmanaged memory. You can write, for instance, a parse method which turns a string into an integer, and you make it consume a span or a memory, and suddenly you have a method which can operate on unmanaged memory and managed memory without having to write it in a duplicate way. That's very important. That's a new way of abstraction that Microsoft introduced here. In addition to that, Microsoft issued a bunch of rules that you have to follow if you work with memory, because it turns out dealing with these classes can lead to a lot of problems, to many of the problems that we try to get rid of with the garbage collector. Let's take a look at these rules. The first one is the ownership rule. Only one owner is responsible for lifetime management, including destroying the buffer. You always have to be very clear who is the owner of a certain piece of memory. And now I'm not talking about the piece of memory that the garbage collector cares for. I'm talking about the piece of memory that you explicitly have to care for. For instance, unmanaged memory that you allocated because you want to be fast. All buffers have a single owner, I told you that, but you can transfer ownership. If I create a bunch of memory, unmanaged memory, I can pass the ownership on to another function, and then this function is now responsible for cleaning up the memory. If this memory isn't cleaned up, it's their fault, not my fault, okay? If I transfer the ownership, and that's the third one, I must not access the memory anymore. If I give it to somebody else and I say, it's now yours, do whatever you want with it, this guy can immediately free it, so I am not allowed to access it anymore. That's the kind of rules that were stated for ownership. However, there can be multiple consumers of some memory. It can be a read-only or a write-only. There is read-only memory and memory of t and so on. And as I told you, a single piece of memory can have multiple consumers. You have to care for synchronizing that. Synchronizing readers is simple. Everybody can read at the same time. Synchronizing writers, we all know it's hard. Finally, we can also speak of a kind of lease. Lease means that we can give somebody a piece of memory for a certain amount of time, and if the lease times out, the receiver of the lease is no longer allowed to access the memory. With that, we can apply the rules of the garbage collector to the lease, and when the garbage collector cleans up the lease or the lease gets out of scope, I'm no longer allowed to access memory, something like this. Do these rules sound complicated? Well, the first one or two, maybe not. The other, well, maybe. Let's take a look at some code. Here you can see, first line here, let's draw here so we have it on the video too. The first line that you see here is a usual piece of memory. We say memory of bytes. It's a new byte. It's managed by the garbage collector. It's really trivial. We never have to free it. Nothing bad can happen. But the beautiful thing here is that we have here the possibility to allocate memory from unmanaged memory, and sometimes we need that if we want to be fast, if we want to interop with some low-level stuff. And the interesting piece of code is that one. See that one? We now can use the memory abstraction to access unmanaged memory. And we have a memory of byte here, and we have a memory of byte here, so it's possible for us now to write code, especially here, this method, do something with a span, without caring whether do something with span operates on managed or unmanaged memory. C# offers an abstraction that works with unmanaged memory, with managed memory, and to be more specific, we are not going into details, span can even work on arrays that live on the stack. So I can pass in a pointer to a memory on the stack and still my method works. You know why Microsoft did that? Because they wanted to speed up especially ASP.NET and things like that. It turns out when you get some memory from a low-level network driver, it's not managed memory. And what did they do until now to write a web server in C#? They copied the unmanaged memory into managed memory. And what did they do then? They applied methods like .substring and things like that. And a .substring method, string is immutable, copies the code, copies the string. And the string is copied and copied and copied. It works perfectly fine. But copying the memory over and over and over again takes time. And the garbage collector has a lot of pressure on it. And that destroys our performance. And with C#7, these abstractions make it possible to keep the memory in unmanaged space. It's fine. We now have abstractions that can work directly on this unmanaged memory, and that is pretty nice, as long as we follow the guidelines that I told you before, because somebody has to free this memory, otherwise we are in deep trouble. Good. This is another API. I will quickly go through it. Can you remember what I told you about the array pool? We shouldn't allocate memory again and again and again. We should reuse memory to reduce the pressure on the garbage collector and keep our memory safe and so on. It's also possible to define a memory pool, which is more a lower level data structure. And here you see this memory ownership. I can say, hey, memory pool, please give me 100 bytes. And if I get it, I am now the owner. You see that one? I am the owner. And I'm on the same time, I am the consumer. And now we write a little bit of code and apply the rules that I told you before. What we can do, as you can see it here, we can call a method and pass in some memory. And with that, we are still the owners, but somebody else is now allowed to consume our memory that we have rented. Get the idea? That's the idea of consumers and owners. Now if we write another method which takes in the IMemoryOwner interface, we really pass on the ownership. Now we are not allowed to free this memory. We are not allowed to give it back. Because we passed on the ownership, this guy here, this guy is now responsible for freeing the memory. We handed over the ownership. That's this set of rules that I told you before, applied in a piece of code. Okay? This is pretty new C#, and yeah, you can find this code now over and over in more lower level algorithms. So what is C#'s solution to our memory management problem? And then we'll invest the rest of the, 20-25 minutes or so in Rust. Okay? C# solves this problem by offering a bunch of helper classes and abstractions on a framework level, on a library level. You get interfaces, you get classes, and very important, you get rules. Follow the rules and everything is fine. For me, this is not perfectly okay, because it just sounds like a little bit of better C++. As programmers, we have to sit down and write better code. Every day we have to stand up and say, today I will write better code that has no memory vulnerabilities in it. And we have seen in the first slide that this simply is not enough. It's not enough. We are not good enough as humans in compiling code and making sure everything is fine. Entering Rust. Rust, one very important concept of Rust is that you are going to hate it because you get so many compiler errors. But the good thing is, if your program compiles, there is a very high chance that it really works. And that's good. So the idea of Rust, and from now on we will take a look at Rust code, not a little bit C# to make, again, the comparison, but most Rust code. In Rust, all these things like classes and interfaces and abstractions and rules, they are gone. They implemented all these memory concepts, these protections in the language, not in the framework. And the compiler has the responsibility to check these things at compile time. You do not need to follow rules to make sure your code is safe at runtime, because these rules are enforced at compile time. If you mess something up, you will get a compiler error, not a runtime error. That's the whole idea of Rust in terms of memory management. Now let's take a look how that looks like. In Rust, every variable, every value that is assigned to a variable, let's put it that way, has a clear ownership. And this ownership, as I told you, is now defined in the compiler, in the language. There can only be one owner. And if you pass on the ownership to somebody else, you cannot use the variable anymore. Can you remember what I told you about C#? That you can pass over this IMemory ownership and you must not free it? Well, you should not free it, but you can. In Rust, you can't. When the owner, the variable, goes out of scope, the value will automatically be dropped and memory will be freed. Rust will make sure of that. There is no garbage collector. If your variable goes out of scope and you are owner, then the memory is going to be freed. You don't need to free it manually. Now let's take a look at a little bit of code. First Rust code for today. I hope you can read it in the back. Is that okay somehow? If it's too small, please let me know. I can zoom in. I have a zooming tool installed at my laptop. Now, this is the main function as you can see it here, and I'm creating a vector of integers. This is just a macro, so this means macro create a vector. A vector lives on the heap, and we have a memory called, we have a variable called numbers, and this variable numbers is just a pointer to the heap, okay? And then we just print the numbers. It would print square brackets 1, 2, 3, 5, 8. This would be the output on the screen. Now what we can do is we can assign, let's draw here on the screen, look at this line here. We can assign numbers to other numbers, and guess what? We passed the ownership. Let me show you that again. Here the variable is numbers. Now we pass the ownership to other numbers. If we would try to access numbers anywhere from here down, we will get a compiler error. Rust will immediately say, no, you are no longer owner, numbers is dead, you don't have it anymore. It's now called other numbers. Other numbers, of course, can be used, no problem. So as I told you, if we try that one here, that one, it will not compile. It will not only crash at runtime, well, it cannot crash at runtime because there is no runtime. Okay? By the way, if you download my slides, and I will happily share them with you, I will share them through Twitter or I don't know, anywhere. If you can't find it, just send me a note. You will find here, down there, links. Nearly every sample has been, I copied the sample onto read execute print loop REPL.it. You can just click on it, you get the code immediately, and you can play with it immediately. Okay, just try the code and make sure that it really doesn't compile. However, what we can do is we can clone, as you can see it here. Okay, here I clone the other numbers. And therefore, because I clone it, I can still access cloned numbers and other numbers. That's fine, we can still do that. Okay? But ownership clearly defined. Next step, ownerships and functions. Again, we have a vector. I don't need to describe a vector anymore. You already know that. And as you can see here, we have now a consume function. Please note that one. And this consume function receives a vector. Rust, in this case, or generally, only knows call by value. Pointers are just another value, okay? In this case, we are passing in the vector, and as I told you, the vector lives on the heap, so we are just passing the pointer to the vector into this function. But as you can see here, maybe you followed the arrow here, by calling this method, we passed ownership from our main function to the consume function. Now, if numbers gets out of scope, here, the vector is automatically freed because now our consume function is the owner of the vector. Can we still try to access the numbers up here? Oh, sorry. Can we still try to access the numbers up here? No, that's no longer possible. The same is true with a function that produces something. Take a look at the second function here. Maybe it's hard to read from the back. Let me zoom in a little bit for you. You can see this produces a vector. It produces a vector by filling it with some numbers. Very simple. By the way, this is the syntax as you can return values from Rust. There is no return statement. You just put an expression as the last statement in your function, and that does mean return numbers. Okay? This is a producer. Now, this producer is currently owner of this vector. But by returning this vector, the ownership goes back to the main method, and now the produced numbers are owned by main, and they are going to be freed when we access the main method, because the owner is now the main method. Understand what I mean? Transfer of ownership between different functions. A consumer does not absolutely need to take ownership. We couldn't write meaningful applications if we always pass on ownership. So there must be something else. And this is called references and borrowing, especially borrowing. Let me show you what that means. Again, our good friend, vector. This vector is printed, as you can see here, just on the screen. Nothing special. But now we have a consumer, and please note that this consumer here gets a reference to the vector. Not the ownership, but just a reference, and with this, we, the main method, keep the ownership, and we only borrow the vector to the function. So now the function consume can access the numbers, but only in a read-only style. It is a read-only borrow. It is not possible. I will zoom in a little bit so that you can see it a little bit better. This is not possible because borrowing a reference does not mean that you can write to this variable. It does just mean that you can consume it, that you can just read from it. So pushing something onto the vector isn't possible. And it will not give you a runtime error, a compile time error. Okay? Good. And these compile time errors, by the way, are pretty nice. Let me finish this slide and then we can immediately take on your question, okay? Now here you see another option. What if the consumer wants to write to this variable? That's possible too. In that case, we have to specify that this is a mutable reference. Now it still is just a borrow, but it is a mutable borrow, okay? So somebody can write to it. And the important thing is that if I borrow something to somebody in a mutable way, I cannot borrow this thing at the same time to somebody else in a read-only or also mutable way. That's not possible. Rust will make sure that this cannot happen. Okay? Question?
So how does the compiler know it pushes a write operation?
Because deep down, somewhere, somebody has to write to this memory. And it figures out automatically that push writes to this data structure. And you also, for implementing low-level data structures, you also have some additional, more advanced things, like, I don't know, ref counting, pointers, smart pointers, and so on, unsafe blocks, and so on. You can always press the exit button. You can always take the red pill instead of the blue pill and do whatever you want. So it is possible to let Rust know that this is really a writing function. This would be out of scope of this talk. We don't have enough time, and maybe I am not well enough educated in terms of Rust already to answer it to the full extent. But for now, let's just assume Rust knows. Okay? Let me show you an example where borrowing saves us a lot of trouble. You see, this is a so-called, I call it broken iterator. Maybe you had that in other languages. This does the following. It's an asynchronous algorithm, okay? Let's start from here. We have, let's see here, we have an asynchronous function. You see that here? So we have a vector inside of an async function. Then I do the following. I call down here another async function, sum, and this just iterates over the vector and calculates the sum. And just to make things a little bit more interesting, you see, I'm waiting for a little bit of time during iterating through the vector. Maybe we access a database or some files or do some complex mathematical operations, whatever. It takes a while we are stepping through this vector element by element. And now I will do something which is very, very bad. While at the same time my iterator is walking through the vector, I am manipulating it in the main function. So now we have a problem. The iterator would be broken. It's no longer possible to continue walking through the vector because the vector has changed and therefore very bad things will happen. And this is not possible in Rust. Why is it not possible? Because here we pass in a borrow, and here we also pass a borrow, but this is a mutable borrow, and this down here is a read-only borrow. And what did I tell you? It's not possible to have a mutable borrow and a read-only borrow at the same time. Compile time error. This code doesn't compile. Get it? Compare that with C#. This is C# code, very old C#. I have a list, something similar to a vector. I have an asynchronous method, exactly as in Rust here. I go through this enumerator, here you see it, with a for each loop, also waiting a little bit while iterating through this list. And at the same time, please note this one, nope, I have to go one, come on, now it works. At the same time, I'm adding a number while iterating through the list of numbers, and guess what? C# is perfectly fine with that. It will allow you to add something to the collection, and it will crash at runtime. So Rust protects you from this mistake. Okay? That's the idea of borrowing. You might ask yourself, okay, if I do async programming, how should I communicate between different threads? And Rust for that has multiple options, and one of the most useful options are channels. There is in the base class library of Rust a so-called channel, and in this case I'm creating a channel of type integer, and what I get back is a tuple, two values, sender and receiver. Sender, I can use it to send something in the channel. Receiver, I can use something to read from the channel. Then I can create a receiver, very simple loop. As you can see it here, I'm just looping over the receiver. Let me quickly show you a little bit of this Rust code, because it's at least for me, when I was starting new with Rust, it was a little bit strange. What you see here is a loop, of course, and then we use the match statement. The match statement here calls the receive function. And this receive function can give back either, okay, everything is fine, I have a result for you, or it gives you back error, something bad happens, here is some error information. And in Rust, something like this is an enumeration. That's a little bit strange. An enumeration in Rust can have parameters. Every enumeration value can bring some parameters with it. So receive returns an enumeration consisting of OK and error. OK has some payload bringing it with, and error has some payload bringing with it. So therefore, this match statement is really mentioning all different enumeration values and consuming the parameter, the payload of the enumeration value, and in this case I'm just printing it. So this is the receiver, pretty straightforward code once you understand what enumerations and the match statement is in Rust. And now let's see how we can produce some values in a different thread. Again, a little bit of Rust syntax here. This is a lambda function in Rust. Between the two pipe symbols, we can write some parameters like we typically do in braces, and afterwards we would have a fat arrow. So in other languages, this would be something like this. This would be like how it would look like in C#, okay? It's just the syntax. But the interesting thing, what we have here, is this move here. Move means that the closure variables, the captured variables, especially the sender, are are copied are now owned by the child thread. So the ownership of the sender is transferred into the child thread. So now the child thread can use the sender of the channel to send information. And now we have what we wanted. We have an asynchronous process up here sending some data, and we have another thread in a loop consuming this data without having any problems with borrowings or shared memory or semaphores and data races and all this stuff. The channel is a safe way of communication between one thread and the other thread. And the ownership principles and so on, they still apply. So what? What is the conclusion? C# has learned a lot of new tricks. They have learned that memory management, managed memory management, is a great thing. It gives you a lot of stability, but it doesn't solve all problems. Think of the broken iterator, for instance. Think of the dispose pattern, where I can free multiple times. And I can create code that is not very stable, let's put it that way. The garbage collector is, performance-wise, pretty costly. So now C# has introduced new types with which we reduce the number of times where we need to copy memory. And the results are pretty impressive. With the latest version of C#, a new JSON parser, for instance, was introduced, which is 2 to 3 times faster than the old one. The old one wasn't bad, it was a very, very good piece of software, but they didn't have the memory abstractions like memory and span and the necessary underlying possibilities of the framework. But it turns out that if we do that, we still run into a lot of memory problems because we just have loosely defined rules that we have to adhere to, but we can't screw it up. Rust, in my point of view, I'm by far no Rust expert yet. I find it a very interesting language. I'm looking into it and I'm looking forward to my first real big projects implementing with Rust. But at the same time, even looking at this language, I immediately understood why Rust is currently in Stack Overflow's developer survey #1 loved technology, in front of every other developer technology that is currently in the Stack Overflow survey, including my good old friend C#. So I now understand why Rust is really interesting, because it combines efficiency and zero-cost abstractions with safety. And this was just the tip of the iceberg that we scratched on when looking at Rust. Rust has a lot of additional interesting features, especially for low-level, system-level programming. So Rust protects us by giving us more compile time errors and less runtime errors. And that's especially important when you do system-level programming. Think of IoT scenarios where you have to write code that runs for a long time in a very stable way. This is why I think that Rust is really a language for the future, and I'm hoping that a lot of innovation will take place there, and a lot of companies will take a look at it and maybe apply it. That is what I wanted to share with you. A little bit of comparison memory management in C# and Rust, showing you a little bit of Rust code, giving you an idea what this borrowing and ownership stuff is all about. With that, I think I've kept my time. I have 1 minute and 18 seconds left. So time management was good. My content is up. That's always a good combination if you run out of content and run out of time at the same time. I hope you enjoyed it. I'm happy to take questions, but we can also move the questions outside to the buffet and beer and drinks and so on. Thank you for having me. Thank you very much.